The focus of this paper is to help artists art-direct fluid sims, like this example here. An animated boat on a body of water is a common scenario. Computation limits force us to only simulate a window around the boat, but forcing the simulation to interact with the unsimulated water is difficult. Practitioners often use naive approaches like collision objects, but this improperly accelerates the simulated fluid. This can be solved by using an open water boundary that effectively seeds in front of the domain and sinks in back of the domain. Within a flip solver, doing this accurately is not straightforward. We show how to accomplish this in a flip simulation by introducing a control construct, the Fluxed animated boundary method, which describes the shape and velocity of outlying fluid at the boundary. Here, we choose a rectangular shape and a zero material velocity, creating an implicit source and sink. Moreover, the fab achieves even more general usefulness as it can have arbitrary animated shape and prescribed material velocity. To better understand fabs, let's look at some 2D examples. Shape and material move at the same velocity, causing no sourcing. The fab stays in place, but the material velocity causes sourcing. Similarly, a fab with non-zero shape velocity but zero material velocity also sources. Additionally, relative velocity can create all sorts of combinations. Now in 3D, let's consider container fabs. Here we create a window to a static water. Here both the material velocity and the shape velocity are matched. Here the material velocity and the shape velocity are perpendicular. A skilled artist can even use fabs to create water creatures. Here a static shape is used for the fab. To derive the velocities, the painted flow lines are used as a guide, and additional curl noise is added to create interesting detail. When simulated, the natural sourcing and sinking behavior of the fab makes a compelling simulation. The particles can then be meshed into a final result. When producing waves, correct velocities are important. Just hand animating them to match the shape does not work well. Stokes' wave, on the other hand, have special geometry and velocity structure. Using these velocities as the material velocity for a fab allows the 3D sim to match a wave train. Enforcing Stokes' velocities creates a stable wave shape. However, adjusting the material velocity allows us to change the Stokes steepness parameters. By exceeding the critical steepness, the wave will break. This can also be done in a 3D flip sim. We can even cause a barrel behavior by varying the Stokes modification along the wave. The particles are then meshed and lastly we create a whitewater pass. This technique was used to create final production shots such as these. While we use a variant of Tessendorf's spectrum-based deep water, we introduce a novel texture tile generator that automatically chooses tile sizes and frequency bands. This allows artists to easily set up spectrums that are periodic tiling artifact-free, even during large zooms. Now we show how the entire boat pipeline works. We start with a TMA sim and create a boat animation using a simple buoyancy-driven rigid body simulation. This input is pre-filtered to match the Nyquist limit of the sim. Then the geometry is eroded to make a fab shape. We then prescribe the fab material velocities. This allows us to create a flip sim. Artists then mesh the particles into a surface. We can then add whitewater. And finally, produce a beautiful render. Here are more beautiful results from our method. Our method can even sail off into the sunset. Thanks for watching.